and a page with small chunks. So we have the first element contains pointers to a PG info list, followed by information about particular pages. So malloc free for the free pages, and first for the first page of the multi-page chunk, and follow for the next page of the multi-page chunk. And again, for a page which is in use, it will have a pointer to its page information. More on this later. So free pages are stored in a sorted doubly linked list based on address, and adjacent free pages are coalesced, and only a pointer to the first page is kept. So this is stored in the page free information. This page free information block is stored using malloc itself, so it mallocs a chunk of memory to store the page free information. This allows the page to be swapped out when it's not in use for a long time, because the allocator just checks the page free information if it should use a chunk or not. So this is an example of the page free information block. So for a page free, we have the next and previous, which store the doubly linked list of free pages, a pointer to the free page itself, and to the last free page. So the first two free pages have been coalesced, so there's only one page free for that area of free pages. And it also contains the size. So the second free page just has page free information, which has and the beginning of the page and the end of the page point to the same page, because there's only one in this area. So as you can see here, the page free information is stored in an area which stores chunk of that size. The chunk layer is the other layer of the PHK malloc. So it has three different types of chunks: small, medium, or large. Large chunks are chunks which are larger than half a page. These are allocated on a single page. And so it will search for a page on which the object will fit, and then set malloc first and follow in the page directory. And that's all the information it keeps for a large page. For small or medium chunks, these chunks are rounded up to the next power of 2, and on a page which contains a particular size of chunks, it will only store chunks of the same size. So for every small or medium page, it stores a page information chunk, and for small pages, these are stored at the beginning of the small chunks. However, for large pages, they're stored again using malloc. And the entry in the page directory points to this page information. So another example. So we've got 3 pages here. Page 1 and page 2 are medium-sized, and page 3 contains small chunks. So the page directory for that, well, page 1 and page 2 contain chunks of the same size. So the page directory for chunks of that size points to the linked list of page informations for that chunk, for that page. And the directory entry for example, for the page with small chunks is stored in that particular page in the page directory. Page information contains the following fields. So the next pointer points to the next page information for the linked list for pages of that size. It contains a pointer to the page itself. And it contains the size and some other information, which I'll not describe here except for the bits. Array, this is an array which denotes if a particular chunk on a page is free or not. So if a chunk is in use, a bit will be set to 1 for that particular chunk, and if it's not, it will be set to 0. Okay, so since PG infos for medium chunks and PG free structs are stored together with normal chunks, they could be overflowed when an overflow occurs, and could be used to do code injection attacks. We'll demonstrate this using a PG info chunk. So what happens is, for PG info, is we make the page field in the chunk point to the target memory. So this is the normal layout. So when an overflow occurs, we make the page point to the return address. And and we modify the bits array to make all the chunks seem free. So when eventually that page is accessed for a chunk of that page, it'll return our target memory as a valid chunk. As a result, the attacker will be able to write into that information as if it was just memory he allocated. So in this case, we'd overwrite the return address with whatever we wanted to. We can also have an off by 1 using PG infos. So in this case, we'd overwrite the next field of the PG info. And instead of pointing to the actual PG info, we'd point to a fake one. And in the fake one, we'd have the page again point to our target memory location. And eventually, when the first PG info's page is when the first PG infos page is full, the fake PG info would be used to return the return address as a target memory location. So for PHK malloc, it's vulnerable to heap overflows and off by 1s. However, it's not vulnerable to double frees because a check is done before freeing if the chunk is free or not. Okay, we'll describe one more allocator, which is BIM's garbage collector. This is a garbage collector for C and C++. It's conservative, so that means if it thinks value in memory, if it thinks a memory address is in use, it'll not free it, even though it might not be in use. So if it looks like a pointer, it won't free it. This garbage collector will automatically release memory during its garbage collection phase to the system that is no longer needed. As a result, no dangling pointer references should be possible because the allocator manages the memory for the programmer. However, if the programmer does explicitly free memory, dangling pointer reference could occur. So there's a difference between large and small chunks in this allocator. So large chunks are larger than half a page and are rounded up to page size. Small chunks are allocated in pages, and again, as with PHK malloc, these pages are divided into chunks of the same size. So an allocated chunk, unlike the other allocators, only contains data. However, a free chunk contains a pointer to the next free chunk. So again, the same attack could occur. So if an attacker can overflow an in-use chunk and the next chunk is a free chunk, he could overwrite the next pointer and make the next pointer point to a target memory location. Eventually, when the allocator reallocates the free chunk, it will return the pointer's target as a valid chunk. Usually, this is an off by 4 attack. However, it could happen that this is an off by 1 attack when there's no padding. A double free can also occur on BIM's garbage collector if the programmer explicitly frees memory. So if chunk 2 is free twice, so chunk 1 is pointing to chunk 2 in this case. If chunk 2 is free twice, it'll be placed at the beginning of the list again. And while chunk 1 still has a pointer to chunk 2. So when chunk 2 is reallocated, it will be writable. So the attacker can change the next pointer. But chunk 1 will still point to chunk 2, so eventually the allocator will return it as a valid chunk, will return next as a valid chunk, and again, the attacker could overwrite an arbitrary memory location. So our conclusion for Böhm's garbage collector is that it's vulnerable to heap overflows, off by 1s to maximum, and generally this heap overflow is just an off by 1 to a maximum off by 4. And a double free is also possible if the programmer explicitly frees memory, which it shouldn't do, but then again, it shouldn't have any overflows either. So our design for a more safe allocator is that on most modern systems, code and data are loaded into separate memory locations. And if we apply the same to chunk information and chunks, we could store the chunk information in separate contiguous memory and protect this memory by using guard pages. However, to associate a chunk with a particular chunk information, we'd use a hash table. So the hash table contains pointers to a linked list of chunk information, and these are accessed through the hash function. So we implemented this in a prototype called DistriNet memory allocator, which I'll be releasing later tonight. And we based this implementation on Doug Leah's memory allocator. So this is kind of what the memory layout would look like. So we've still got the text segment. And in the data segment, we have the data section and the BSS section. And for the normal heap section, we have the chunks. And in the maps, in the area where maps are stored, we have a map to hash table, and we have mapped chunk information. When the program starts, well, when the program first calls malloc, we map a hash table which is large enough to contain all possible values stored in the hash table. This is pretty large. It's usually 96 megabytes. However, this is just virtual address space because when an area is mapped, it will be used as virtual address space, but when a page is actually used, it will only be allocated by the operating system. So we divide each page into 256 possible chunks, and our minimum chunk size is 16 bytes. So we then separate these chunks into 32 groups of 8 chunks. So for every group in the hash table, we have 1 entry. So this means we have maximum 32 entries in the hash table for every page. And we access 1 element of the group through a linked list of maximum 8 elements. So this is what the hash table would look like on the left. So it contains only pointers to chunk information, and beside that we have the actual chunk information. Hash next is used to store the linked list of maximum 8 elements. And again, we have the forward and backward pointer as the original allocator does to have the doubly linked list of free chunks. We store the size of the chunk, and we store our pointers to the actual chunk. So the hash function is designed this way. So to find a chunk information from a chunk, we subtract the start of the heap from the chunk's address and shift the result 7 bits to the right. And then we go over the linked list until we have the correct chunk. We can do this by just comparing the chunk information chunk to the chunk we were looking up. So we also actually need to manage the chunk information area. So we do this by mapping a fixed area of 16,000 chunk elements. And whenever a chunk is removed, so for example, if 2 chunks are coalesced, 1 chunk information will no longer be used, so they will be stored in a linked list of free chunk information. And when we need a new chunk information, we'll just get it from this list of free chunks. If none of the chunks, if we don't have any free chunks, chunk information, we'll just allocate one from the fixed map. If the fixed map is empty, we'll map extra memory, and this region is always protected by guard pages. So we've done some tests to see what overhead we'd have using this memory allocator.